Let us recall what we have did in previous lecture. So in the previous lecture, we were discussing about the Bessel's equation. The Bessel's equation can be written as, or it can be expressed as x square y double dash plus x y dash plus x square minus p square y equal to 0. And the solution of this Bessel's equation, we know it is known as Bessel's function. So the Bessel's function is Jp of x, which is summation of n running from 0 to infinity minus 1 raised to n upon n factorial into p plus n factorial x by 2 raised to 2n plus p. We have proved that. Then the next one is the property of this Jacobian. Here p is a greater than or equal to 0 we have. So to define this p plus n, it also may possible that this p plus n is not an integer. So in that case, we have to extend this, or we have extended the definition of the factorial as a gamma function. So in general, this Jp of x, now it can be possible to express as any positive real number. For that also we have discussed in previous lecture with the regard that this gamma of p, it can be expressed as 0 to infinity e power minus x power p minus 1 dx. If p is greater than 0, then it is defined like this. If it is not an integer and if it is negative, then it will be defined like p into p plus 1 upon p plus n minus 1. If p is negative and it is the negative integer, it is in between integers for some n belongs to n, and it is not defined if p or minus p is belongs to this set. So in that way, we have discussed that this gamma function is defined to extend this definition for any real number p. With that help, we have proved that this Bessel's function are, if I replace p by minus p, then they are linearly dependent. That means we have proved that Jp of x is equal to minus 1 raised to p Jp of minus x. If p is an integer, if this p is an integer, positive integer, or 0, p is already positive. So if it is an integer, positive integer, then we have proved that this quantity also. And next, we have discussed that the general solution of this Bessel's equation, if p is not an integer, so that is very important concept that we have discussed, that if p is not integer, then the general solution can be written as C1 Jp of x plus C2 Jp minus x. Because we have already proved that if p is an integer or positive integer, then these two things are linearly dependent. So it is not integer, then we have this is the solution in general form. And the secondly, if it is an integer, that means if it is a positive integer, then the solution y is equal to c1 jm of x plus c2 ym of x, where jm is the Bessel's function, and this where ym, that can be calculated as limit of p tends to m yp of x, where yp of x is cos p pi jp of x minus of minus jp upon sine p pi. So this way we can express a general solution of this Bessel's function. Now in this lecture, we are going to discuss some properties of Bessel's function. So the next concept is the properties of Bessel's function. The first property that we are going to discuss is so that d by dx of j0 of x is equal to minus of j1 of x. And second one, so let's say A is this, B is d by dx of x into j1 of x is x into j0 of x. Let us try to prove these statements. So in the first statement, we know that jp of x, that is the Bessel's function, which will be summation n running from 0 to infinity minus 1 raised to n upon n factorial into p plus n factorial x by 2 power 2n plus p. Now if I want to calculate d by dx of j0 of x, that means I need to substitute p equal to 0 into this series. That means j0 of x equal to summation n running from 0 to infinity minus 1 raised to n upon n factorial into n factorial, that is equal to 0 with substitute. So it is n factorial into n factorial x by 2 power 2n. And what is j1 of p or j1 of x? By putting p equal to 1 here, we will have that is summation n running from 0 to infinity minus 1 raised to n upon n factorial into n plus 1 factorial into x by 2 power 2n plus 1. So now by differentiating this j0 of x, that is our objective, is to calculate differentiating j0 of x. So d by dx of j0 of x will be applying this derivative here. So instead of the first quantity will be constant, so that summation will start with 1 to infinity minus 1 raised to n upon n factorial square into 2n by 2 raised to 2n into x raised to 2n minus 1. So this can be expressed, or this can be simplified as x running from 1 to infinity minus 1 raised to n upon. This 1 2 is cancelled with this, and 1 n is cancelled here. So I can write this is n factorial into n minus 1 factorial. And combinedly writing this x and by 2 together, we can write this is 2n minus 1. Now replace this n by n plus 1 because I need to start this index with 1. So that's why I'm replacing n by n plus 1. We get d by dx of j0 of x is equal to summation n running from 0 to infinity minus 1 is to n plus 1, because instead of n we have to replace n plus 1. So this is n plus 1, this is n plus 1 factorial into, here you will have n factorial into n factorial. Here this is x by 2 power 2 into n plus 1 minus 1. So finally what we get, it is minus of summation n running from 0 to infinity minus 1 raised to n upon n factorial into n plus 1 factorial into x by 2 power 2n plus 1. And we can observe that what is j1 of x is exactly minus 1 raised to n summation of minus 1 raised to n factorial into n plus 1 x by 2 power n plus 1. So it is this. So this is minus j1 of x that we can have. Into the second property that I want to prove is this d by dx of x into j1 is equal to x into j0 of x. So let us try to do that. So now to prove the b, we'll observe what is d by dx of x into j1 of x. So this is d by dx of, now we know that what is this x, j1 of x, so that is we know it is minus 1 raised to n upon n factorial into n plus 1 factorial into x by 2 power 2n plus 1, and into this x is there, so I'm just multiplying x to this series, and we can just writing this is or rewriting this one is summation n running from 0 to infinity minus 1 raised to n upon n factorial into n plus 1 factorial x into this one. So this 1 upon 2 power 2n plus 1 I'm just writing as it is, and this is x power 2n plus 2 we have. Taking this derivative inside, we'll have summation n running from 0 to infinity minus 1 raised to n upon n factorial into n plus 1 factorial 2 power 2n plus 1 into 2n plus 2 into x power 2n plus 1. So this 2 can take common, and this n plus 1 is cancelled out. 1 n plus 1 is cancelled out with this. So this will be summation n running from 0 to infinity minus 1 raised to n upon 2 into n plus 1, and this is n factorial into n plus 1 factorial, and this 1 2 is if I can cancel out, or I can write down this is x by 2 power 2n plus 1. So this is the things we got, and this 1 n plus 1 I can take cancel with this one, and this is n factorial. બૂટ થાય છે પેન ડ્રાઈવથી હા આખી સિસ્ટમ વિન્ડોઝ રીઇન્સ્ટોલ કરી એટલે ચેકિંગ આવે છે, પેલું શું કરે છે, વેરીફાઈ કરે છે બધો ડેટા. भागाकार number. So this is what I want to prove is this, that x into j0. J0 is this. Okay, that is minus 1 raised to n factorial into n factorial x by 2 power 2n. So that is 2n plus 1 is there. Sorry, where it goes? Yeah, 1 2 is cancelled with this 2. So it is, we can write down, and x I can take out. So that is summation n running from 0 to infinity minus 1 raised to n upon n factorial into x by 2 power 2n. And this 2 is cancelled with this 1 2 here. So that's why this is, we got, it is x into j0 of x, which completes the proof of that. Now here I am giving you some exercise to do it, or you just try to draw the graph of the j0 of x and j1 of x in some of the this some of the software which is available online. Can try to draw a graph of these functions by your own. Also, one can write down what is the value of this j0 of x and j1 of x, okay, and try to draw the graph of that. The value of j0 and j1 we can have from this. J0 is this, j1 is this, and put the series into that and try to draw various values of x. What will be the graph of this j0 and j1? Okay, so that I'm giving you as an exercise to do it by yourself. And nowadays there are lots of softwares are available, so using that you can able to draw that. Next property, that is the second one. In that, the first one will say that, prove that between any positive 0 of j0 of x, there is a 0 of j1 of x. What does that mean? Any positive 0 of j0 of x, there is a 0 of j1 of x. Second one is prove that between any positive 0 of j1 of x, there is a 0 of j0 of x. What it says, prove that between any positive 0 of j1 of x, there is a 0 of j0 of x. So what do you mean by 0? If I have a function f of x, what I can say, x0 is the 0 of this function if f of x0 is 0. Then x0 it's called the 0 of this function f. So here is j0. What is the 0 of j0? If j0 of z0 or x0 is 0, then it's x0 it's called the 0 of this. So here our objective, or we need to prove that the 0 of j0 between any positive zeros of j0, there is a 0 of j1 of j. So let us say, let a and b be any two positive zeros of J0 of x. That means J0 of A is 0 and J0 of B is 0. And here we have assumed this A is less than or equal to B. So with this A is less than or equal to B, that is the condition. What we have to prove is there exists some number C which is in between this two AB such that J1 of C is 0. That is our objective. That is this statement says. Between any two zeros of J0, there is a 0 of J1. So between this A and B, there will be some number C which is in, it is a 0 of that. So to prove this one, let us try to use the Rolle's mean value theorem. Okay, what is Rolle's mean value theorem? Let us state that. So if f is a function, the first one, f is continuous function on closed interval AB, f is differentiable function on open interval AB, and third one, f of A is equal to f of B, then there exists a C in between AB such that f dash of C equal to 0. So to use this Rolle mean value theorem to prove the first statement. See here, we know that this function f or Jp is a continuous function on closed interval AB. We know that because it is expressed in the power series. So this Jp of x is a continuous function in the interval AB. Jp of x is differentiable on open interval AB. And the third one is Jp of A is equal to Jp of B equal to 0. So it's satisfying all these three conditions of the RMBT. Therefore, by Rolle's mean value theorem, what we have J0 dash, there exists a C in between AB such that J0 of C is equal to 0. But what is J0, J dash of 0? That means the derivative of this J0, which we got from this previous property, that the derivative of J0 of x is minus of J1 of x. So due to that, we can write down this as J1 minus of J1 of C is equal to 0, which will implies J1 of C is equal to 0 for some C in between. For some C, it is belongs to AB. So we can say that C is the 0 of J1. So that means thus any or between any two positive zeros of A and B, of zeros of 0 A and B of J0 of x, there exists C in between AB. That means A is less than C less than B. There are such that C is the 0 of J1 of x. That is was the statement A. Now the statement B says that prove that any positive zeros of J1 of x, that is a 0 of J0 of x. So ultimately we have to prove that if you can consider two zeros of J1, then there will be a one in between them, there is one zero of J0. So let A and B is any two positive zeros of J1 of X. That means J1 of A is 0 and J1B is also 0. Let us consider the function f, which is defined over AB to R as f of x is equal to x into J1 of X. Now this x into J1 of X is a continuous function on open. Again, we are applying the Rolle's-Mean value theorem to prove this. So since this capital F of f is continuous on closed interval AB, it is differentiable on open interval AB, and it satisfies. And the last one is f of a is equal to f of b equal to 0 because x is 0. Because J1 of A is 0, J1 of B is 0. So that is also 0. So therefore, by Rolle's theorem or Rolle's mean value theorem, we get there exists C in between AB such that f dash of C is equal to 0. But what is f dash of C? What is f of x? Is x into J1 of X. That is the derivative of this f of x is d by dx of x into J1 of X. But previously we have proved that x into J1 of X is x into J0 of X. So that will implies x into C into J0 of C. But C is not 0 because A and B are non-zero. So that's why J0 of C is 0. So it says that there exists some C which is a 0 of J0. So which proves this results of in between two zeros of J1, there is a 0 of J0. So if you have any doubt in this, you can ask me.